Hello all. We will now take a departure from considering algorithms in inner product spaces and instead delve into the mirror dimension, which is not Euclidean but might better approximate the geometry of some problems. So let us take a look at how we can go beyond inner product spaces in the analysis of algorithms. So far we have seen various algorithms and their oracle complexity results. A key feature of all these results was that the oracle complexity depended on parameters such as B, L, LF, mu, etc. However, all of these parameters were defined with respect to a certain norm. Remember that distance from the optimum was with respect to a certain norm, and likewise Lipschitz continuity and smoothness were with respect to a certain norm, and so on. That implies that the choice of the norm plays a critical role in determining the performance of an algorithm. Indeed, to improve the oracle complexity, we just need to have a well-chosen norm for which these parameters are lower. Conversely, the geometry of the function may be such that the standard inner product norm may not be well suited. In other words, the same function may appear to be ill-conditioned with large condition number when those quantities are defined for norms that arise from inner product space. So naturally, the application of standard projected gradient or subgradient descent algorithms may give us poor oracle complexity. However, the same function may be well conditioned when it can be considered within a different space. That space would be such that the parameters of the function defined with respect to that space would be much more regular. We have seen an example of this earlier in the context of preconditioning, where an affine transformation of the vector x made the function regular. In general, however, that space may not necessarily be an inner product space. In fact, distances in that space may not necessarily be defined using norms at all. Clearly, we cannot apply classical projected gradient or subgradient descent methods because these algorithms are only defined for inner product spaces. So we need a modification of these algorithms that can handle arbitrary distance metrics. Let us take a simple example, just for demonstration purposes. We have already seen that the negative entropy function is given by f of x equal to sum over I from 1 to n xi log xi, where the domain of f is delta n omega, where x belongs to non-negative orthent, such that entries of x are greater than omega and sum up to 1. So omega is a small positive number that ensures that none of the x values are equal to 0. We already know that the function is convex and Lipschitz continuous. Let us calculate its Lipschitz continuity constant LF for various norms. Recall that LF is the bound on the gradient norm of the function. So here we have that the ith entry of the gradient of f of x is 1 plus log of xi. Therefore, we can see that the L1 norm of the gradient, which is equal to sum over I from 1 to n, absolute value of 1 plus log xi, is less than equal to n times log of 1 by omega minus 1. Similarly, L2 norm of the gradient is equal to square root of summation over 1 to n square of 1 plus log of xi, which is less than equal to square root n times log of 1 over omega minus 1. Finally, the infinity norm of gradient of f of xi is the maximum of the absolute value of 1 plus log xi over all I, which is less than equal to log of 1 by omega minus 1. So for L1 norm, the gradient norm is order n, while for L2 norm, it is order square root n, but only order 1 for infinity norm, if we are talking about a large n. Recall that the complexity of projected subgradient descent was order b LF square by epsilon square. Now if the problem is high dimensional and we are using classical projected subgradient descent, then the oracle complexity would increase with n square or n. The problem is in fact ill conditioned for large n because LF square term in the oracle complexity will dominate. In contrast, suppose that we were using algorithm whose complexity depended on the infinity norm of the gradient, then the oracle complexity would be independent of n and therefore not so large. In summary, this example demonstrates that the oracle complexity depends on the distance metric in terms of which the oracle complexity has been characterized. Let us look at various assumptions. We are still considering problems of the form x star equal to argmin of x in calligraphic x, f of x, where calligraphic x is closed and convex such that it is in the relative interior of the domain of f, and f is proper closed. Initially, we will start considering with the assumptions AC that f is convex and AL that f is LF Lipschitz with respect to some norm. In other words, we are considering a basic convex setting with possibly non-smooth functions to start with. We have already seen the projected subgradient method that works in this scenario. As we have already mentioned, we are interested in a general algorithm that operates in a completely different space, where distance is not necessarily measured using a Euclidean norm. Recall that we have already seen a generalized version of the gradient descent, which did allow for an arbitrary norm. However, we did not analyze its performance. Moreover, we want to operate in a space which may not even use norm as a distance metric. The reason for that is to allow functions whose geometry is not similar to any norm. In order to develop the intuition of the mirror descent algorithm, recall the projected subgradient descent algorithm, where the updates take the form xt plus 1 equal to projection of xt minus eta t gt, where gt is a subgradient of f at xt. Let us use the definition of the projection operation and expand and write these updates as xt plus 1 equal to argmin over x in calligraphic x norm square of x minus xt minus eta t gt. In projected subgradient method, this norm is an inner product norm, so we can expand this and drop the constant terms so as to obtain that argmin over x in calligraphic x 2 eta t inner product of x minus xt comma gt plus norm square of x minus xt. Then we can scale the objective and add other constant terms so as to write it as argmin over x in calligraphic x f of xt plus inner product of gt comma x minus xt plus 1 by 2 eta t norm square of x minus xt. So if you recall, we have already seen this way of writing the updates. Here we have a linear approximation of f at xt, and to it we are adding this proximity term that encourages xt and xt plus 1 to be close. The last term is essentially not letting xt plus 1 to be too far from xt, and in this way ensuring that the quadratic objective is a good approximation to the original function of f at xt. The main idea of mirror descent is to use an alternative function in place of the last term. Overall, the goal of the last term is to improve the quality of the approximation. So if the quality of the approximation can be improved using a different function instead of the squared distance, then we can expect the algorithm to perform even better. In the mirror descent, we are particularly interested in considering general measures that tell us how two quantities are related. For instance, if the optimization variable is a probability mass function in n-dimensional space, we know that the distance between two PMFs, P and Q, in Rn is better measured using KL divergence or Kullback-Leibler's divergence, KL, P, Q, rather than the Euclidean norm of P minus Q. You may recall that the KL divergence is not based on the norm, and in fact KL divergence is not even symmetric. That is, KL divergence between P and Q is not the same as the KL divergence between Q and P. The Bregman divergence provides one such class of measures and is defined as d phi of x comma y is equal to phi of x minus phi of y minus inner product of gradient phi of y comma x minus y. Here phi is a proper closed, strongly convex and smooth function. The mirror descent involves carrying out the updates xt plus 1 equal to argmin of x in calligraphic x f of xt plus inner product of gt comma x minus xt plus 1 by eta t d phi of x comma xt, where we have replaced half norm square of x minus xt with d phi of x comma xt. Note that if we take phi equal to half norm square of x, then the Bregman divergence becomes half norm square of x minus y. So for this choice of phi, the mirror descent is exactly the same as projected subgradient descent. In general, however, phi can be any smooth and strongly convex function. Henceforth, we will assume that phi is some mu phi strongly convex function. The KL divergence is a specific example of the Bregman divergence which is widely used. To see this, consider the negative entropy function phi of x equal to summation over I from 1 to n xi log xi, with domain of phi equal to x in non-negative orthant such that 1 transpose x equal to 1. For this case, it can be seen that d phi of x comma y is phi of x minus phi of y minus inner product gradient phi of y comma x minus y, which can be written as summation over I from 1 to n xi log xi minus summation over I from 1 to n yi log yi summation over I from 1 to n 1 plus log yi times xi minus yi. So now we can group these and rearrange so as to get minus summation over I from 1 to n xi plus summation over I from 1 to n yi plus summation over yi from 1 to n xi log xi by yi. Finally, since x and y are in the probability simplex, the first two terms cancel, so we get the KL divergence. This is also called the relative entropy, and clearly it is not symmetric. So KL x comma y is not equal to KL of y comma x, and therefore it is not a distance metric. Let us also look at how the mirror descent updates look like when using the KL divergence. The updates are written as xt plus 1 equal to argmin over yi greater than equal to 0, f of xt plus inner product gt comma y minus xt plus 1 by eta t d phi of y comma xt, such that summation over yi equal to 1. So we have solved this kind of problem with single constraint many times before, so we will skip a few steps. We will associate Lagrange multiplier with the equality constraint. Then the Lagrangian is given by L of y comma lambda equal to f of xt plus inner product gt comma y minus xt plus 1 by eta t d phi of y comma xt plus lambda times summation over I yi minus 1. Now we can write down the first order optimality condition, and let us ignore the non-negativity constraint for a moment. Also observe that the gradient of d phi y comma xt is equal to gradient of phi y minus gradient of phi xt. So these updates will give rise to an algorithm called the exponential gradient descent. To derive it, observe that the first order optimality condition can be written as gt of I plus 1 by eta t log of xt plus 1 of I minus log of xt of I plus lambda equal to 0. Or equivalently, xt plus 1 of I is equal to xt of I times exponential of minus eta t times gt of I times exponential of minus eta t lambda. Note that we did not worry about the non-negativity constraint, and the solution here is already non-negative. However, we need to adjust lambda such that the entries of xt plus 1 sum up to 1. That is, summation over I from 1 to n xti exponential of minus eta t gti exponential of minus eta t lambda is equal to 1. So this implies that the exponential of eta t lambda is equal to summation over I from 1 to n xti exponential of minus eta t gti. So now substituting, we get that the algorithm updates are given by ith entry of xt plus 1 is equal to ith entry of xt times exponential of minus eta t gti divided by sum over all j from 1 to n xtj exponential of minus eta t GTJ. As you can see, this is a very interesting and quite different from the classical gradient descent. Here the effect of GT is modifying xt in a multiplicative manner. This is called the exponential gradient descent, and you can imagine that it is well suited for situations where the optimization variables are probability mass functions. So that is all for this video. There are in fact many other examples of Bregman divergence functions, and we'll not be able to look at all of them, but you should get a general idea. In the next video, we will start looking at the properties of the mirror descent update.